All right, and so if we want to kind of figure out some properties for stream 3, we could use our entropy balance to find the entropy for stream 2, and that'll tell us the entropy for stream 3. Okay? All right, and so to find the entropy for both stream 2 and stream 3, we're going to use the thermodynamic properties chart for our refrigerant of Freon 22. Okay? All right, and so these plots can look a bit intimidating, so I kind of want to go through first and break down exactly how to interpret them. Okay? And so in these plots, the first thing to look at are the axes. So the y-axis here is going to be pressure, and the x-axis is going to be enthalpy. All right? Then, for each of the different lines, so we're going to start over here, you have lines going in different directions, okay? And the angle, or the direction that the line is going to indicate a different property. And so, for lines that kind of go up and down initially and then curve off to the left, like these, or if we go here, this one, these refer to temperature, okay? So the temperature lines are the ones that go up and down, okay? For the lines that go left to right, kind of this way, these refer to the specific volume of the refrigerant at different conditions, okay? So these lines. And then the lines that go diagonally down, kind of from top right to bottom left, these are for enthalpy, or these are for entropy, okay? Right? So that's the entropy of the refrigerant at different conditions. And so as I mentioned before, just like in the steam tables where if you knew, for instance, the pressure and the enthalpy of your system, so if you knew the pressure and then you knew the enthalpy, wherever they intersect here, that allows you to figure out different sort of thermodynamic properties. So in this case, they intersected here, and so that would correspond, we see, that sits on the entropy line of 1.80 kilojoules per kilogram Kelvin, right? And so by knowing those two things, that allowed us to then get entropy, right? And so, once again, if you just know two different thermodynamic properties, that will allow you to figure out any other property on this chart, okay? And so that's what all the lines on this right-hand side mean. On the left-hand side here, this deals with the refrigerant that's saturated, okay? And so in this kind of big sort of parabola-looking shape, right in the middle you have something that's known as a critical point. In a couple of weeks we'll talk more about exactly what that is. But on this arc, everything that's to the left, that sits on the kind of outermost part of this arc, those correspond to the properties of the saturated liquid refrigerant. Okay? While everything on the right side of this arc corresponds to the saturated vapor. All right? And so if you're told you have a saturated vapor and you're told the temperature, so those are two different thermodynamic parameters, you would just go to this line and you would find the corresponding temperature, and then that would tell you, things like the vapor pressure or whatever the enthalpy is at that condition, okay, or at that temperature and phase. All right, and so these plots are still kind of weird, and so to make this more concrete, let's revisit our problem, and let's use the plot to find the entropy for stream 2. So for stream 2, we're told it's at a temperature of 0 degrees Celsius and that it's a saturated vapor. And so, since we're told it's a saturated vapor, that means we're going to want to look on the right-hand side of this plot. Okay, so this is where the saturated vapors live. Right? On this right-hand side of the plot, we see the different numbers, and those numbers correspond to different temperatures. Okay? So we know we have a saturated vapor, and we want to find on the saturated vapor line where 0 degrees Celsius is, right? And it's right here. Okay, so I'm going to mark this in red. All right, so we found the intersection of the saturated vapor and 0 degrees Celsius lines. All right, now that we know where that occurs, what we could do is we can now find, if we go from, or it's better if we go from top right to bottom left, this diagonal will tell us the entropy of our refrigerant at these conditions, okay? So here's where our intersection is, and so I'm going to draw a line that goes up and to the right. Okay? And so when we go up and to the right and we look at these labels, we see that essentially our intersection is coincident with a diagonal that corresponds to some number between 1.74 and 1.76 kilojoules per kilogram Kelvin. All right, so that, once again, this is the entropy line. All right, and so for this number here, it's actually kind of closer to 1.76. So I'm going to call this 1.755 kilojoules per kilogram Kelvin. So it sits on that entropy line. So S2 is going to be equal to that. Furthermore, if we look at our intersection here, if we just draw a line going straight down, we see eventually our line will intersect these specific enthalpies here. And so we find that for saturated vapor at 0 degrees Celsius, H2 is going to correspond to about 405 kilojoules per kilogram. Okay? And so with these plots, what we have to remember is we can't, we're reading it off a plot. So we can't be, super precise because we're kind of estimating, and where our line is going to end up. But in any case, from here, by knowing where this intersection is, we're able to read off all of our other thermodynamic properties. Okay? And so going back here, so from Freon 22 chart, we were able to get that H2 is equal to 405 kilojoules per kilogram, and that S2 was equal to about 1.755 kilojoules per kilogram Kelvin. And then from our entropy balance, we also know this is equal to S3 for the reversible case. Okay? All right, so now we figured out one property of stream 3. All right? But in order to get all of the thermodynamic properties for it, we need to somehow figure out one other thermodynamic property outside of the plot. Okay? All right, and so to do that, we're going to leave the compressor for a bit, and we're going to start thinking about the condenser. Okay? And the reason we're going to do that is because for the condenser, we know information about stream 4. Okay? We know its temperature, and we know its phase. We know it's a saturated liquid. And so because we know two properties here, that means we could get any other thermodynamic property off this chart. Okay? Specifically, we know it's a saturated liquid, and so that means we want to look at the left-hand side here. And we know that it's occurring at a temperature of 25 degrees Celsius. So that intersection would be right here. All right, and so since we can now, draw out that intersection, we can now use this plot to kind of figure out any sort of other thermodynamic property. All right, and so one thermodynamic property that is going to be interesting is going to be the vapor pressure at which the saturated liquid occurs. And that vapor pressure we could get if we just draw a line that goes straight to the left. Okay? And we see that the vapor pressure for the saturated liquid refrigerant at 25 degrees Celsius is going to be about 10.5 bar. Okay? So here for condenser, outlet is saturated liquid at T4. T4 is equal to 25 degrees Celsius. And so from the plot, we're able to get that the vapor pressure, or P4, is 10.5 bar. Okay? Alright, so we know the pressure for stream 4. How is that going to help us out with stream 3? Well, if we look back at our assumptions, one of the things we assumed is that the condenser is isobaric. That is, as a stream goes in and a stream goes out, the pressure is not going to change. And so we were able to figure out what P4 is. And so for this condenser, if we know P4, that means we could figure out what P3 is. Okay? So since condenser is isobaric, that means P3 is going to be equal to P4, which is just going to be equal to 10.5 bar. Alright, and so now we know the pressure, the vapor pressure, or the pressure of stream 3, and we also know its entropy. And so now for stream 3, we have two thermodynamic properties. And so since we have two thermodynamic properties, that means we should be able to get any other thermodynamic property we want for stream 3. Okay? And so to do that, once again, what we want to do is find the intersection of our pressure and entropy lines. Okay? And so for pressure, or for the entropy line, we have it essentially right here. And for the pressure line, all we have to do is kind of, draw it until it intersects the entropy line we drew earlier. Okay? And so that intersection is here. Okay? All right, and so we know where those two things intersect. Okay? And so now that we know where the intersection is, what we want to do is we want to figure out what enthalpy this intersection corresponds to. And to figure out what enthalpy it corresponds to, we know that the enthalpy is the x-axis here. To figure out what enthalpy it corresponds to, we just need to draw a line straight down from here. Okay? And we see that based on our enthalpy intersection, H3 for the reversible case is going to be equal to about 425 kilojoules per kilogram. Okay? All right. And so now that we have that enthalpy, so from Freon chart, H3 is going to be 425 kilojoules per kilogram. All right? And so in our energy balance, which we wrote up here, what I'm going to do is I'm going to divide the mass onto the left-hand side. And so for the compressor, the reversible compressor, which would just be H3 reversible minus H2, and we have all of those properties, so this is H3 rev, which we have here. H2 we looked up earlier. So if we take the difference of those, it's just 20 kilojoules per kilogram, right? So this is essentially a sort of specific work. All right, so we don't have work or the mass flow rate yet. But nevertheless, what we can do is we could still use the efficiency we were given earlier in order to kind of tell us what this work over mass flow rate would be for the irreversible case. Okay? And so that's because for the efficiency, right, for a compressor is this. Right? Once again, WC reversible is what you want, but due to this efficiency, this is what you actually have to put into the system. Okay? All right, and so in this ratio, this is just based on the definition of efficiency. We know the efficiency here. We have this value from our energy balance. And so what we could do is we could rearrange this equation. Essentially, we would just be taking that 20 kJ kg and dividing it by the 0.75. And we get that our work, in this case, for the irreversible, the work over the mass flow rate would be 26.7 kilojoules per kilogram. Now that we know that value, we could go back to our energy balance and we can rewrite it in terms of the irreversible enthalpy. Okay. All right, and at this point, the only unknown we have is this. So we could solve for H3 irreversible. And when we do, we get that it's slightly higher than it is for the reversible case. So it's about 431.7.